So far in the course, we sort of discussed the basic properties of optical fibers and how they guide light and the properties of the modes, etc. Right, and so the remaining part of the course will be mostly just discussing various types of devices made using optical fibers. Okay. So today we'll start with a very important one known as erbium-doped fiber amplifiers. So they are optical amplifiers. Optical fiber based. Which are used to boost or increase the power in an optical signal, right? And so this was a very important development in the late 1980s and basically enabled sort of the global connectivity of the fiber optic network, right? And basically the modern internet where anybody from anywhere in the world can access any information quickly, right? So you can imagine, even with a very low loss coefficient of the optical fiber, right, like 0.2 dB per kilometer, once you start going to long distances, hundreds of thousands of kilometers, the loss is a serious issue, right? So for example, with 100 kilometers, you get 20 dB loss, which means you're only remaining with 1% of your transmitted power, right? If you go 200 kilometers, that's 40 dB. That means you're only left with 0.01% of your transmitted power. So you can see that. So once we talk about terrestrial, continental, or intercontinental distances, then we need some way to boost the optical power in the signal, right? Otherwise, basically, we won't have enough power at the detector. So the development of this EDFA was very important, and nowadays, like for long links, you have these EDFAs placed periodically, let's say every 80 kilometers or 100 kilometers or so, to boost the signal powers. Okay, and the nice thing is that it's optical fiber based, right? So basically, the same fiber that is used to carry the information, just you can splice these amplifiers right in the transmission lines, right? Yeah, so we'll see how they work. Right, so before the development of these optical amplifiers like EDFAs, people used to have to convert the optical signal to an electrical signal, right? And then electronically, like clean up the signal, boost it up, and then convert it back to optical, and then send it along. Okay, so that you can imagine. First of all, is expensive, requires a lot of components. Second, also that it is limited, right? Because the speed, etc., bandwidth would be limited because you need to convert to optical to electrical and back to optical. But with these optical amplifiers, you don't need to do anything. Sort of like the signal keeps transmitting along the fiber. Just periodically, it encounters these amplifier stages, which are also in fiber, right? And the optical signal automatically gets boosted. Okay, so imagine you have some optical communication link, right? So you have a transmitter, and typically based on where these amplifiers are placed, they're known by sort of different names. So for example, if you place so each of these triangle denotes an optical amplifier, or specifically an EDFA. So if the amplifier is placed just after your transmitter to basically boost up the transmitted power, this is known as a power or booster amplifier. Okay, and then you have periodically placed amplifiers along the optical fiber, long optical fiber that is carrying the signal. So these are known as inline amplifiers. Okay, and then sometimes we also use an amplifier just before the receiver to boost the signal that we get from the photo detector. Okay, to improve basically the signal to noise ratio that of the electrical signal that we finally get. So that is another pre-amplifier. Okay, so the construction of all of these are basically the same, right? They consist of a length of optical fiber where the core is doped with these erbium atoms. Okay, but depending on these applications, their like specifications might be slightly different in terms of noise and gain, etc. So yeah, so basically, if you look at one of these amplifiers, what's inside, right, is just so a length of optical fiber. Okay, so where the core is doped with erbium. So if I look at the cross section here, so you have the core here. The core typically is doped with some concentration of erbium. Okay, and so the fiber is typically few meters to few tens of meters. So let's say between 5 and 50 meters in length. Okay, and basically these erbium atoms have energy levels such that basically it can enable amplification of optical signals, specifically in this telecom wavelength range around 1.55 micron, which is what is used for long fiber links, right? So how do we get the amplification? Basically, so there's another, there's a diode laser within the amplifier, okay, which is sort of also coupled into this main fiber, okay, and it's co-propagating with your, so the main signal is coming from, so some optical fiber is carrying the signal, right? So that signal by the time it comes to the amplifier is very weak. Right? So this diode laser acts as a pump. So the optical signal, as you say, this is in the telecom wavelength range. So typically for EDFAs, the wavelengths are let's say between 1.5 and 1.6 microns. Right? So there's a pump laser in here which is typically the pump wavelength is at 980 nanometer. Okay, or sometimes 1480 nanometer is also used, but 980 nanometer is more popular. So we'll see why. Okay, so this so for amplification, basically this medium of the erbium doped inside this glass acts as a gain medium, right? And so you know from basic laser operation, right? So how gain happens is that you create some kind of population inversion, right? Where you have more atoms in some excited state compared to ground state, and then that transition leads to, due to simulated emission, leads to amplification at that particular wavelength. So basically you need a mechanism to create the population inversion, so that's what this pump laser is doing. Okay, and so because of this amplification, now at the output your signal is amplified. Okay, and so there's a coupler in here is known as a WDM fiber coupler, which basically combines the incoming signal at the telecom wavelength with this pump laser at 980 nanometers, so that in this section here, you have both the pump and the signal co-propagating in the fiber. Okay, we also see later in the course how these couplers are made and okay. Anyway, so basically, if you look at the energy levels of this erbium atom, right? So once you dope it inside glass, they exist as erbium ions. Okay, erbium 3 plus ions inside this silica matrix. Okay, so they have some energy levels. So there is some ground state here. Okay, so there are three main energy levels which are of concern for us for the EDFA. Okay, so this ground state is denoted as the energy level is this 4I15 by 2. We don't need to concern ourselves what this nomenclature actually means. It's just some name for some level for now. Okay, so basically there are three levels that are involved. Okay, so this 980 nanometer pump basically sends atoms from this ground state, where, like under steady state, basically most of the atoms are here, right? So the 980 nanometer pump sends atoms to this excited state here, which is very short-lived. Okay, so there is a fast relaxation to this intermediate level. Okay, and this intermediate level is basically a metastable state which has a long lifetime. So typically, this is about 10 millisecond lifetime. Okay, so basically, if you have a strong pump, it pumps atoms here and they quickly come and relax here. So basically, the atoms end up settling here. Okay, and if the pump is strong enough, then you can end up having a lot of atoms here, right, compared to here. Right, so let's call the number of atoms here, let's say N1, this is N2, and this is N3, right? So N3 is typically 0 because this lifetime is very short-lived. So typically, as soon as an atom comes here, it quickly goes there. Right, so for a strong enough pump, let's say you could achieve where N2 now becomes more than N1, then basically you can get stimulated emission gain for this transition. Okay, and so if you look at the wavelength corresponding to this mg difference, this wavelength typically lies. Okay, it could lie anywhere in between, let's say 1530 to 1610, right? Because this level is broad and this level is also, the ground state is also broad. It consists of many sort of vibration levels in between, within itself. Okay. So depending exactly from where here it comes and where it relaxes, the width of these bands gives that sort of wavelength range. Okay. So basically, depending on the consumption, you can amplify wavelengths between this range. So typically, there are two types of EDFAs that you would see in the market. One is called a C-band EDFA. Okay, so that amplifies typically wavelengths from 1530 to 1570. And the other is the L-band EDFA. So that works between usually 1570 to 1610. Okay, and then so basically you have to do slightly different tweaking for it to work efficiently at these wavelengths versus these wavelengths. So typically there are two different devices which are used. But the basic construction is the same. So typically, like if you look at the gain profile, right, it will have some bandwidth here. So for the C band EDFA, so the gain could, these amplifiers can be built to provide really large output powers, like up to few watts, and the gain can be as high as like 30 dB, right, over this wavelength range. Right, so the gain bandwidth is broad enough that, for example, you could also amplify multiple different wavelength channels within the band. Right, so this is basically like a 3-level laser system that you might have studied in your basic lasers course. Okay, so one thing to mention here is, so yeah, so typically this is how the EDFA is operated with a 980 nanometer pump, but sometimes you'll see some EDFAs where instead of 980 you use a 1480 nanometer pump, okay, which basically doesn't go up to this third level, but just goes up to the top of this second level itself. Okay, and then you have some relaxation within the second level, and then amplification here. Okay, so you can see that the pump laser is now much closer to the amplification wavelengths, 1480. But typically, like the noise performance, etc., of this 1480 pump laser is worse compared to the 980 pump. I mean, the advantage is that the 1480 is close to these wavelengths, right? So, so for example, both the pump and signal can travel in this same fiber with modes which are similar to each other, well overlapped, right? Whereas 980 is a very different wavelength from 1550. So the mode profiles would be significantly different. Okay? But the performance that you get with 980 pump usually is much better. So most EDFAs use 980 in terms of noise and yeah, mostly in terms of sort of the noise performance. Okay, so basically what is happening as this pump and signal are traveling through this erbium-doped fiber. Right, so you have some core region here which is also doped with this erbium. Right, and then you launch. So after the coupler, now you have pump and a. So you have a pump mode and you have a signal mode, right? Pump, signal. Now co-propagating through the fiber, right? So now the pump gets absorbed. So if you look at so plot the pump power as a function of propagation distance in this fiber. Basically, the pump keeps reducing because it's getting absorbed. Right? And if I now look at the signal power, so typically the pump power is really strong, right? The launch pump power is very strong compared to the weak signal that we want to amplify, right? So the signal starts out somewhere very low here, right? So if I've got signal power on this axis, then the signal gets amplified because of stimulated emission here, right? So if the pump is strong, now you have this population inversion condition and you get amplification for the signal. So it starts increasing, okay, and it gets amplified up to a certain distance. But then you can see that the pump is also now being reducing in power, right? After some point, the pump is so low that beyond here you're not getting this population inversion. Okay, so now basically even the signal wavelengths just get absorbed because you have more atoms here, they just get absorbed. Okay, so beyond a certain length, when the pump power has become low or pump has become depleted, this will start absorbing again. Okay. So note that these two are not on the same scale, right? So because pump is much stronger, as I said. So if I wanted to plot them on the same scale, the pump will be up somewhere here, right? And the signal will go like that. Because the pump is strong and the signal is weak that we are trying to amplify. Anyway, so basically there is an optimum length, right, of the fiber which will give me maximum gain. So because of pump depletion, it's not that if I just keep using longer lengths of this erbium-doped fiber, I'll get more and more gain. Because after some point the pump gets depleted and the signal also starts getting absorbed. Okay, so there is some optimum length always, given other parameters like input pump power, etc. There's an optimum length which will, give you the maximum. So this optimal length typically lies in the few meters or tens of meters range. Okay, so let's see how this amplification happens. Starting from some basics. Okay, so basically we have these two energy levels between which the transition corresponding to the signal wavelength is happening, right? So whenever you have an atom with two such energy levels, right? So there are three things that can happen as it interacts with light propagating through the medium, or the photons propagating through these medium, right? So one thing is, so if you have an atom in the excited state, right? It can just spontaneously decay to the lower state, right? Emitting a photon of energy which is equal to the difference in the energy levels. Right? So the wavelength or the frequency of emission can be calculated from the difference in energy. So this is spontaneous emission, right? So the atom in the excited state just spontaneously decays to the ground state. Then you could have stimulated emission. So if there are already some photons present in the medium, that can cause the atom to, or they stimulate the atom to come down from the excited state to the ground state, right? And so because of this, the atom also emits photons. So basically your optical field is now higher because right, the optical field stimulates the emission of more photons. Okay? So this is the mechanism by which gain is happening. Okay? So this is stimulated emission. Right, and of course, you could have an atom in the ground state which just absorbs the photon to go to the excited state. Right, so this is just absorption. Okay, so we can write simple rate equations for each of these three processes, right? So for spontaneous emission, the rate of change of the atomic number in this higher level 2 we just write like this. Okay, so the upper level has some lifetime tau sp. So this is the spontaneous emission lifetime, or the lifetime of the upper state. Right. So basically, on average, if you put an atom in the excited state, on average, how long does it stay before decay? Okay, and this A is known as the Einstein A coefficient. You might have also heard about. Because it was Einstein who wrote down these equations for the first time. So stimulated emission now the transition is being stimulated by the optical field. Okay, so now it depends on this parameter which shows the strength of the interaction of the atom with the photon. Okay, so this is known as emission cross section, and then it depends on the intensity of the incident field, right? So more photons incident in the medium, more stimulated emission or more transitions downwards they will cause, right? So this depends on the intensity. So I by h nu, right? So this is the you can see this is the, so this is intensity divided by photon energy. So this is the number of photons per unit area per unit time, right? So this is the photon flux which is sort of traveling through the medium, right? So the number of transitions it will cause per unit time depends on the number of photons crossing per unit time. Yes. So the question is, the pump power decreases because of absorption, which causes population inversion. Yes, right. Because remember the pump wavelength is tuned to be exactly equal to this transition, right? So basically the pump is, and most of the atoms are here in steady state, right? So the pump basically gets absorbed and then puts atoms here, and then they quickly come down to here, right? So you deplete atoms from here and then you go out there. So it's this absorption which is causing the pump release. Right, times. So basically in the spontaneous emission, the rate was just a constant depending on some atomic constant, the lifetime here, right? But here now the rate depends on the number of photons, because stimulated emission means the photon is stimulating the atom to come down. Okay, yeah, and this thing is called the emission cross section, sigma sub E. Right, it's called a cross section because you can see it has units of area. Okay, because so this whole thing has to have units of per time. This one here, I by h nu, has units of per area per time. So we multiply by area to get per time. Right? So this has units of area. That's why it's called a cross section. But it's not any physical cross section. Right? You can think of this as sort of roughly the size of the atom. As seen by the field. Right, so it's just a measure of how strongly the atom interacts with the photon. So bigger this number, right, higher your stimulated emission and absorption rate. Right? So you can think of this, so you can think of the atom as some ball and the photon coming in as also some blob, right? And what is the probability that they collide and then this interaction takes place? Right? Depends on roughly, if you think what is the size of these blobs, right? So that depends on this cross section. Bigger the cross section, the bigger the atom appears to the photon, or vice versa, right? So that the probability of interaction is higher. So for erbium atoms in glass, this number is, just to give you some scale, this is about 10 to the minus 25 to 10 to the minus 24 meters square, in that range. Okay, and so if you take different atoms and different energy levels, there are different values for this cross section. There are some atoms which, for certain energy levels, have much bigger cross sections. There are some which have lower cross sections. So that's stimulated emission, and then absorption. Also, I can write similarly. Right, so now absorption is causing a decrease in the number n1, the number of atoms in the ground state. So I can write it similarly like this, except instead of emission cross section now I have absorption cross section. Okay, which is also a function of frequency. Okay, so these three processes are happening within this medium as the fields are propagating. So let's take a small volume element along the propagation direction. Okay, so this is at some distance z, this is z plus delta z, right? So, and the cross-sectional area here is some s. So this is volume s times dz. So here we have some incident intensity I nu z, and at the output the signal intensity changes to I nu at z plus delta dz, right? And inside this volume, these three processes are happening, right? With change in intensity. So, right. So within this volume, so the number of upward transitions or absorptions per unit time just from there, right? So this is per unit volume. So N1 and N2 are the densities, so the number of atoms per unit volume. So basically within this volume, we just multiply with the volume. Okay. So we multiply this rate by the volume to get the total number of absorptions happening in this volume, right? So now, similarly, the total number of downward transitions or stimulated emissions per unit time. Okay, so typically once the you go into the regime of gain where stimulated emission takes over, then this is much stronger than the spontaneous emission. Okay, so you can just assume that the stimulated emission rate is much bigger than the spontaneous emission rate, and the total downward transitions are just given by the stimulated emission. So this is true in the once you go into the gain regime of the amplifier. Okay, so now basically what is the energy absorbed per unit time in this volume? That's basically the total number of upward transitions minus the total number of downward transitions times the photon energy. So each transition, right? So each upward transition absorbs h nu units of energy, right? So basically within this volume, the total energy absorbed would be the difference of these. right, times hν. So this is the photon energy. Okay, so the hν cancels out here, and I'm left with okay. So where this eta is defined as the ratio of the emission cross section to the absorption. Okay. So it's also a function of frequency of wavelength. But yeah, so that's the energy absorbed per unit time within that volume. Just one thing to mention: the spontaneous emission, which you've neglected for now, it basically gives noise in the amplifier, right? Because all these spontaneously emitted photons typically have random phase and also could have different wavelengths to the exact wavelength that you are amplifying. Okay, so basically they add noise photons to your signal. Okay, so when we want to do a noise analysis of the amplifier, then we have to include spontaneous emission. Anyway, so now the energy absorbed in this volume, I can also just write from the change in the intensity, right? So the input power into this volume is the input intensity times the cross-sectional area, right? And the output power is that. So input power minus output power is basically the power absorbed in this volume, which is basically the energy absorbed per unit time. So now if I write this as I nu at z minus derivative right, so I just do a Taylor expansion of this intensity at z plus delta z. So then this just becomes okay. So this thing is basically equal to this thing, right? Both are the same. The energy absorbed per unit time in that volume. So equating these two, we get an equation for the propagation of the intensity at the signal frequency. So you can see that how the signal power or the intensity of the signal wave propagates. I can just write as a absorption coefficient which depends on frequency times the intensity. Right? So this absorption coefficient is the absorption cross section multiplied by this difference of n1 and then n2 scaled by this eta, which is the ratio of the emission to the absorption coefficient. right? So this alpha nu. Right. So now for amplification, if you want the wave to grow with increasing Z, that means this alpha has to be negative, right? So if alpha is positive, that's the usual case that you have, right? Just absorption, simple absorption in a material. But now if this alpha of nu can become negative, then you can see that the intensity will get amplified. And from the expression of alpha nu here, you can see it becomes negative for, so you get gain if you can have this eta times n2 greater than n1, or in other words, n2 if you can make it greater than n1 divided by eta. Right, so this is something like the population immersion condition. Right, so typically eta is close to 1 for most materials in most wavelength ranges. Right, the absorption and emission cross sections are typically close to each other. So this is of the order of 1. So you can see that this gives you n2 greater than n1, the population immersion condition. Right, you need more atoms in the excited state than the ground state for gain. Right, but in certain wavelength ranges, so we'll see for this erbium-doped fiber that this eta can, for certain wavelength ranges, especially so the wavelength range you're talking about, like 1530 to 1600 in that range, actually this eta becomes greater than 1. Okay, the emission cross section is actually higher than the absorption cross section. So you can see actually you can get gain even before n2 greater than n1, right? So typically like eta would be, let's say, between 1 and 2. As the wavelength increases, actually this eta increases. So for longer wavelengths, you start getting gain first because this condition is reached faster, right? Because eta is high. So if you look at this eta or the emission and absorption cross sections as a function of wavelength for erbium-doped, so it looks like this. Wavelength. This is wavelength in nanometer. Right, so we are talking about this range of wavelengths here. And if I plot the cross section, so again this is in 10 to the minus 25 meters square. So the absorption cross section, so cross section peaks at around 1530 or so. 1520, 1530 in that range. Okay, so this dotted line is the absorption cross section. And then the emission cross section looks like this. Okay, so basically you can see below 1530, the absorption cross section is higher than the emission cross section, and then for wavelengths longer than 1530, the emission cross section is actually higher than the absorption cross section. Right, so basically this is eta less than 1, and here eta is more than 1. Right, and you can see here basically the condition for gain actually is easier to achieve the larger eta is. So these wavelengths are amplified easier, and actually the longer wavelengths, this eta ratio is more, so the longer wavelengths amplify first before these lower wavelengths, and then below 1530 it's difficult to get amplification at all. Okay, so that's why EDFAs work from 1530 to 1610 for in this range. So maybe we'll stop here for today. Start with that. So yeah, in the next class we'll see, we'll basically model how the fields are actually propagating in a fiber, right? So we saw here that now the condition for gain. So now we'll actually see the actual situation of a fiber with a doped core, right? And then see basically how the pump and signal fields travel along this fiber, and so with these processes of stimulated emission and absorption happening along the fiber, right? And then we try to derive some propagation equations for the pump and signal, and see again conditions for gain, and try to see like how much amplification you get for given pump power, etc.